Okay, so welcome to today's topic, which has to do with observations, interpretations, and also with making measurements on objects or devices that don't have a digital display. So we make a measurement on something like an electronic balance. It's quite easy to get the right reading. You just look at the digital numbers and write them down, and you're good to go. When you've got an object like a graduated cylinder, a ruler, or a thermometer where there are lines printed close together or even sometimes far apart, it's important to know how to use that device to get the most quality out of your measurement. In other words, how to get the most precision out of the measurement that you make on that object. And a quick glance usually won't do it. There's a few things you want to keep in mind, and after you do it a couple of times, actually it'll get quite quick. But before you do that, there's a lot of things that people don't know how to do quite right, and it becomes just kind of a matter of a new habit for you. So we'll start out with the difference between observations and interpretations first. So what is an observation first? An observation is basic information that you gather with your senses. It could be something like a smell, it could be a measurement with a number involved, it could be a color that you see or observe, but it's going to be something fairly concrete or black and white. In other words, if you look at it and your lab partners look at it, or I were to look at it with you, we would all agree that yes, this object is white, or this object is getting warm, or this object has a mass of 10.00 degrees, rather grams. So the observations that you'll make about things will be fairly straightforward and hard to argue with. You and all of your partners should have basically the same things. By comparison, an interpretation, or sometimes you'll hear it called an inference, is the meaning that you take from your observation. So what does your observation mean to you? This is where it can get rather subjective. In other words, you might see something as an observation, and it might mean or give you a different interpretation than it does something to someone sitting next to you. You might think that it means that carbon dioxide is being produced during the reaction, and someone else next to you might think that it means that some other gas is being made, perhaps. And so the conclusion, or the interpretation is the better word, that you take from an observation can be different for you than it is for your lab partners. And it's important to remember that that's okay. This is why we do labs together. We gather observations in common with each other, and then hopefully go work on it on our own to get our own interpretations from those observations. Why is that important? Well, if you come back the next day and you're now kind of discussing the lab in class, if you've been working on it independently by yourself, and now your group is sort of discussing your interpretations together, you might find that someone else's perspective is very different than yours, and maybe after you talk about it for a while, you'll find out that they were right. And if you'd been thinking and just sitting in a group, maybe that perspective wouldn't have even come up. So it's important to think about doing these things as much as you can after the lab is over, on your own, or in as small a group as possible, so we get the most perspectives. So as I mentioned before, there are two types of observations. The first is a quantitative observation. Now in there you might see the word quantity, which is a word you've probably used and heard of many times before. So a quantity is almost always some kind of numerical amount or observation that you take. So this is a numerical information piece from a measurement that you make, an approximation that you make. It's going to be something like a mass, a length, volume, temperature, time, or anything else that has a number involved. On the other side, we have qualitative observations. Qualitative observations are those things that don't have a number. So something like a color. We can't describe color using a number very easily. We can't describe a smell using a number. Just describing perhaps that a reaction is getting warm in a flask or a test tube, you would say the test tube got hot. Well, that's not a number, but it is a qualitative observation. Texture, you could describe something as being rough. Could be something like your paper towels in the lab, perhaps. One is smoother or softer. That's not a number. It could also be describing how big or small maybe crystals are as they grow during a reaction. Fine crystals versus coarse crystals. That's a very qualitative observation. Even something as simple as the state of matter, solid, liquid, or gas. That's a qualitative observation too. When we're taking quantitative observations, they have to be two things, and you've heard me mention these words already, so we'll hit them a little more formally today. The first thing is every quantitative observation should be accurate. This means it needs to be as close as possible to the correct actual value. Now what is that? Well, let's say a pencil, for example, or whatever you're writing down these notes with. It has a particular length to it, and that length is only one thing. There's only one length for that pencil. So if I handed your pencil to 3 or 4 or 5 different people and ask them to give me the length of it, they might come back, all of them, each of them, with slightly different measurements. And would they all be accurate? Well, probably, possibly, they could all be fairly close to the accurate length of the pencil. So if it were a 15 centimeter pencil, and someone came back and said it was 15.1 centimeters, and another person said it was about 15 centimeters, and a third person said it was 14 3/4 centimeters or something like that, they'd all be pretty accurate, as close as they could be to the real value. If someone said it was 20 centimeters long, well, that wouldn't be very accurate, probably a quick estimate, or they just read wrong on their ruler or something. So accuracy is being correct, or as close as possible to correct. Precision's a little tougher to get your head around at first, and so this is the one we'll talk about and show a little bit more with practice on our graduated cylinders today and other things like that. Precision has to do with two things. The one that we'll use most in chemistry, it has to do with including as many decimal places as possible, or perhaps better is to say, including as many decimal places as the instrument allows. Now, every object that you use to measure, whether it's an electronic balance with a digital readout or a graduated cylinder, a thermometer, every measurement instrument has a limitation on its precision. It can only be so good. This is why you can go online or look in catalogs and buy electronic balances that have 1 decimal place, even some that have no decimal places, just measuring to the nearest gram. Or you could buy electronic balances like we'll use in class that have 2 decimal places. Next door, Mr. Weigum in AP Chemistry has balances with 5 decimal places. And the more decimal places the device has, you might guess, the more expensive it is. And that's very true. As we go up and up in precision, we go up and up in price. And what we need to do is find the balance between the one that we need as far as quality that we need and the one we can afford. What's the one that does the job that we need and does it cheapest? And 2 decimal places tends to be all we need in chemistry, so it's what we use. That's as many decimal places as you can get off that instrument. When we're looking at something like a graduated cylinder, you can't just glance at it. It doesn't say on there 2 decimal places or something. But after you've used them for a while, you'll know how precise that instrument can be. And that's how much precision you need to take from that instrument. The other meaning here you'll see behind the pink bullet is that it can also mean that the measurement is repeatable or reproducible. And that means that if you were to measure an object 5 times in a row, that you would get the same length, for example, each time. It also has to do sort of with the idea of, say, target shooting. If you were to shoot archery, bow and arrow, into a target, if you could put 3 arrows or 3 darts into a dartboard in a very small circle, that's very precise because you're repeating your throw into the same bullseye or the same target spot many times in a row. That's also another meaning for precision. As I mentioned, every tool has a limit to its precision, and as I said, most precise tools are more expensive. So we want to take as many decimal places as possible, as much precision as possible, no more and no less. That's really important to remember that. So for non-digital measurements, using things like graduated cylinders or rulers or other things like that, and we'll practice with a few pictures here in a minute, we want to do several things right, especially with graduated cylinders. Those are the ones that we'll use the most. Rulers are easy to use, but we actually don't use them too often in chemistry. So the non-digital device that you'll use most is almost certainly a graduated cylinder. If you take AP Chemistry, you may also learn about using something called a burette, and we'll maybe use them in here a couple times as well. But what you want to do with a graduated cylinder, remember these things every time. 1, you want to make sure that you set your object on a flat surface so that the meniscus, which is that little curve at the bottom of the liquid makes in the container, is level and even, and you're not getting and thrown off because you're picking it up and holding it in your hand. Second, we want to make a measurement at eye level. So you want to get down so that your eye is at the same level horizontally with that meniscus. That can mean bending over at the waist, bending at the knees, squatting down to it, whatever it needs to be. Unless you're a very little kid, 6th grader or something, probably the lab bench is not eye level for you. So you can get down to eye level and read it horizontally. The third thing is to read the bottom of that curve. And again, it's called a meniscus. There you see that word in bold. It's a pretty important term to know. So if you've never heard that word, or might forget it, maybe jot it down. It's a Latin-looking word, and so meniscus is the curve that the water liquid level makes, or whatever liquid we're using, makes in the container that it's in. And you've probably seen these before, even if you've never thought about them very much. You can see meniscuses even in a glass of water. And then lastly, this is the part we'll practice, is to estimate 1 decimal place, or even just 1 digit, beyond what is given by the graduations, or those little lines, on the instrument. So if we have lines on a graduated cylinder for every 1 milliliter or cubic centimeter, then you need to estimate 1 decimal place past the ones place. If you think back to elementary school math, when you first learned about ones and tens and hundreds and tenths and hundredths and thousandths and things like that, then you remember maybe what decimal places in these places will be. So if my device only has lines down to the nearest ones place, then I'll need to estimate one further than that, which is to the tenths place. If I've got a graduated cylinder that measures to the nearest tenth, it has lines for the nearest tenth, then you'll need to go one further than that to the nearest hundredth. We can even get burettes that go to the nearest hundredth or thousandth, or you'll have to go even one decimal place further than that, and that's for amazing precision, usually with very, very small amounts of liquids. You'll see things like that also in the precision that's used in devices like hypodermic syringes for medical applications or something, where the amount that you're giving a patient through a syringe is critically important, and the amount needs to be just exactly right. Okay, so we're going to look at some graduated cylinders and a few rulers, just to kind of show you how to make measurements by taking one decimal place or one digit more precise or further than what's printed on the side of the device itself. So these pictures are actually from the worksheet that you get in class, and so they should look familiar to you. You can kind of take some answers down as we go along. I'm going to move this guy up just a little bit. You can see your numbers at the bottom there are 1 through 6 to match the ones that are on your sheet. What I'd like to do is actually start not with number 1 here, but with one of the middle ones, number 2, 3, 4, 5. These are all actually sort of more or less from the same graduated cylinder. And the way you know that is that the major lines that are marked with numbers here are to the nearest 10. So on number 2, for example, we have marks here for 30, 40, 50, 60. And for number 4, we have marks starting at the very bottom at 0, 10, 20, 30, and so forth. If you look at number 1, you can see that it's actually got major markings for every 1, or to the ones place. And way over here on number 6, you've actually got major markings to the nearest tenths place, which is kind of unusual for anything that you'll see in regular chemistry. But it's possible. It could be on something like a burette. So as we look at these, middle 4, then, they're all going to be somewhat similar as far as their precision goes, because they're all more or less from the same device. If we could imagine these all being a segment or a vertical section from the same long graduated cylinder, then we'd be making measurements on that one graduated cylinder, and they should be somewhat the same. So I'd like to show you on here is how we make a measurement then on, say, number 2. So if we take a look at number 2, this curve, like we mentioned before, is called the meniscus. And if there are water in a graduated cylinder, especially one that's made of glass, you're going to see a meniscus, a curve, because water has what's called adhesive properties or adhesion. The water molecules like to stick to the glass, and so they almost sort of crawl up the sides. We'll talk more about that when we get to bonding and intermolecular forces and something called cohesion and adhesion. It also explains why water droplets are round, or why raindrops are round, and other things too. But for now, let's just take a look at this little curve or meniscus that the water's forming right in here. If you can kind of take a look then, that line is above 40, certainly. It's even above 41. So if you look really closely, this little line here, this one, represents 41 milliliters. We're going to assume this is measuring in milliliters or cubic centimeters. So here's 41, here's 42, here's 43. Now, let's say we're looking at that curve, and we can all agree that it's more than 40. So I'm going to go ahead and say it's 40-something. And that something, it's definitely at least 41. And many of you will look at this and probably say that this line is actually right at or even slightly above the 42 line. Well, let's say we all agree. Now, if you don't, that's okay. We'll talk about you in a second here. Let's say that we all think, well, it's pretty close to 42. And you probably even would be comfortable if I gave you this graduated cylinder and said, what's the volume in here? You'd look at it and say, it's about 42 milliliters. And you'd be accurate, but you wouldn't be as precise as you could be. And the reason for that is that the line, this little line, tells you 42. So any old person could look at that and say 42. But we need to be able to go one digit further than that, because we need to be more precise. One decimal place more precise than what the device itself tells us. And it tells us 42. They don't mark that little line, but that's what it represents. So you need to go one decimal place further than that. So it's 42 point what? Well, let's say you look at this and said, I think it's just a little bit above 42. What you have to do is sort of imagine between 42 and 43, right in here, that there are actually 10 more small spaces in that little gap. Well, that's pretty small, and so you're going to be estimating it, which is fine. Let's just say I'm going to be right a little bit above it, and so I might say that's 42.1. And you'd be good. That'd be precise enough. You can't go any further than that, because then you'd be estimating 2 decimal places, and that's not allowed. You can only estimate 1. So I'm going to look at that and say 42.1. Now what if my lab partner comes over here and says, no, oops, that's 42, but it's right on the money. So I don't think it's 42.1, I think it's 42.0, and that'd be fine as well. Well, let's say your third lab partner comes along and says, you're both wrong. And this is what I mentioned before, those of you who think that it's not even up to the 42 line yet. So let's erase that whole thing. And let's say, well, I'm a third person. I'm going to come along and say, from my perspective, it's actually a little bit under the 42 line. And so I'm going to say it's only 41 point something. And I'm going to say that something is 9, so 41.9. So that's 3 different measurements, and you could actually be even a little bit more or less than that, and probably still be okay. But if I'd said 41.9, and someone else in my group thought it was exactly 42, and a third person said 42.1, well, we're all being accurate, because those are all reasonably close. We're all being equally precise, which is to 1 decimal place, to the 10th place. And we'd all be fine. These would all be correct answers. You could write those down on your lab table or on a sheet like this, and you'd be perfectly fine. Now, if you said 43.1, you'd be precise the way you should be, but you wouldn't be accurate because this isn't up to 43. And again, we always want to read, like I said before, the bottom of this curve, right at the lowest point. You can't read 43 be way up here. It's nowhere near that high. So if you're to say 43.1, your precision is good, but your accuracy is actually way off. If you were to say 41.1, again, your accuracy is off. If you're to say 42.15, you're accurate, but you're being actually more precise than you're allowed to be. And sometimes that sounds a little weird. Shouldn't we be as precise as we absolutely can? Well, you are when you only have 1 decimal place here, because that's all this allows. If I take a look at number 3, I'm going to clear out some of these other measurements just so I don't have all 3. You only need 1 answer, not all the possible answers. So really any of these would be all right. And they'd be just as correct on a quiz or anything else too. If I were to look at number 3, I'm above the 50, this is 55, 56, 57, 58, 59. I'd say I'm between 58 and 59, and probably so would you. So this is 58 point something, and that something is up to you to decide. Maybe I look at that and say, it's just about half, maybe not quite, so I'll say 58.4. Maybe you say it's 58.3 or 58.5 or something else, but it's going to be 58 point something. If we take a look over here at number 1 real quick, we can tell it's above 12, but this line then is not 13 because 13 is way up here, right? So if you can imagine that this line is 12.1, 12.2, 12.3, 12.4, and so on, then this line, this big one, actually is 12.0. Think about it, right? So that's 12.0. This one's 12.1, 12.2. So if I were to look at this, I would say it's above 12.1, which is this little guy right here. But it's not quite to 12.2, which is this one right here. And so it's between 12.1 and 12.2. I'm going to say it's 12.1 something. And again, that something is for you to decide or for your partners to decide on their own. I'm going to say it's just a little bit above 12.1, maybe not quite as little as it might be. So I'm going to say it's 12.1 and 2/100ths. Okay, right a little bit above. Maybe you say it's 12.11 or 12.13 or even 12.10. You'd want to have 2 decimal places because the lines themselves, as I sort of indicate here, the lines themselves represent the 10th place, 12.1, 12.2 on that device. And lastly, one more example, number 6, is to look at this and say, okay, this is 1.2, this is 1.3, this is actually even 1 more degree precise. So this is 1.20, this is 1.30. They don't print that onto a graduated cylinder because it's sort of, I guess, understood or maybe just cluttered up or something if you add that. But that's what it is. And it's important to recognize that because that means for us that this little mark, which we're right above with our meniscus here, is actually about 1.28 if you count up to it. So this is 1.28 something. And that something is, again, your estimate. So I'm going to say it's more than halfway up. It's about 1.287. Then you might say 286 or 285 or 288. And you'd be all in the same neighborhood at equally precise and just as accurate and good. So what I'd like you to do is finish up the rest of that front page, if you haven't already done that, and go on to the back and try some of those too. It's quite simpler on the back, actually, if we take a look at that, because on the back side, there aren't any meniscus to deal with on each problem, and that helps us out just a little bit. So I guess I'll do one quick example with you on the back. If we take a look at the first ruler at the top, this could be a ruler or a meter stick. It could also be a thermometer if there were a liquid inside to show us the temperature. But it would be the same, more or less the same phenomenon. So if I were to look, say, at position C on this page, You may be a little closer on yours because your page is right in front of you than I can with the screen here. But we take a look at where position C is. It's above 56 and maybe not quite to 57. Hopefully you see it that way too. So if that's the case, 56 but not quite 57 means that for position C it's 56 point something. And that something is, well, between, let's say, a little more than halfway and not quite all the way to 57. So I'm going to call that about 56.8. And again, if you said that was 56.5 or 6 or 7 or 8 or 9, maybe even you see that because your copy's a little more blurry or off than mine, maybe you're seeing it as 57.0. As long as you have one decimal place and you're in the neighborhood of about 56 to 57, you're doing fine. Now, with those few examples in mind, take a few minutes and work on the others on this page as you get it. If I've already handed it out to you, get right to it. If you haven't, hopefully you can come back to these examples and jump right into the page tomorrow. Today's discussion of observations, interpretations, and measurements are brought to you by Diet Cherry 7-Up. Refreshing, crisp, hard to beat. By Townhouse Flipsides Crackers. When crackers and pretzels alone aren't enough. And Easy Cheese, the American version. Guaranteed never to spoil.